Welcome you all to the webinar on grid modernization, technological advancement beyond smart grid, which is conducted by John D. MacDonald, who is a distinguished, I hope I'm audible. Yeah, sure. A distinguished speaker of IEEE and kind of the big contribution for us. John is conducting this session for IEEE PS Sri Lanka section, which is a event we do in collaboration with IEEE Central Region subsection and IES Telecommunication and Electrical Committee. So on behalf of all the IEEE and Sri Lanka section and also IEEE PS Sri Lanka chapter, I warmly welcome John for this webinar. And thank you very much for accepting our invitation. So before starting, I would like to give a small opportunity for this ISL as well to introduce themselves as they are one of the organizing part of the committee. Dushanta, I think you are available.
And power and Sri Lanka ISL and our social community to manage this program. So I should John Janagayanaka for
I think Dushanta was breaking a little bit, but at the end, I will give another opportunity for him to talk if it was not clear. So before making it delayed again, so I'm going to introduce the speaker, but it's a very long profile because he's a very expert in the field. So, but I'll try to do my best on it. So John D. MacDonald is founder and CEO of JDM Associations. And John has 50 years of experience in the electric utility transmission and distribution industry. John received his BSEE and MSEE power engineering degrees from Purdue University and an MBA degree from University of California, Berkeley. John is a life member of IEEE, a member for IEEE in 53 years. So member of IEEE HKN and also Tau Beta PI introduced 55 years ago. Members of Delta Sigma Phi fraternity and was awarded the IEEE Millennium Medal and the IEEE Power and Energy Society Excellence in Power Distribution Engineering Award. And the PS Substations Committee Distinguished Service Award and PS Meritorious Service Award, and the list goes on. So it speaks for your expertise itself, John. And also I would like to introduce him as the past president of IEEE PS and also the vice president of technical activities of the U.S. National Committee of SIGRE and the past chair of IEEE PS Substations Committee. So given all the experience, it's an honor to have you here, John. So without further ado, I would like to give you the floor to conduct this session, which our audience will be much interested in hearing. Thank you so much.
Thank you. Yeah, thanks, Akila. Always good to see you. Good to see you again.
You too. Thank you.
Let me share my screen, okay? And I'll bring up my slides. Can you see the slide?
Yes, we can.
Yeah. Okay, good. Well, I was gonna highlight some things about modernizing the grid. Okay. So I'll highlight these, and then if you know, we'll have time for questions, or if you want some more detail, make some notes, you know, jot some notes down so you don't forget, and we can cover those at the end. So I won't go into a lot of detail here because I want to cover quite a bit of material. Okay. First thing though, it's a little bit more about myself. And one important thing is we really you may not know this about me, but what's very important to me is my health. And I made a life-changing decision 14 years ago of eating healthier and working out with a trainer. I just had a very tough workout just about a half hour ago. Every morning I work out with a trainer and run races. This is a 5K race in the lower right with my trainer, where I took a second in my age group. The top photo, my son had just gotten his MBA at Duke University, and we celebrated the morning after graduation with a 5K run, 5K race. So I really emphasize that your work is much better when you're in good health and you feel good, you eat healthy, and you exercise on a regular basis. And I've been doing that for 14. I'm 72 years old now, and I can beat all the younger people that I exercise with because I really pride myself on being in good shape. Okay. So these are the topics I'm gonna highlight with respect to modernizing the grid. First topic is some trends. This is important. We've with microprocessor-based devices, they have two-way communications capability. So we integrate those into what we call a holistic solution. Holistic means enterprise-wide, and a solution is a set of technology components that are integrated together to meet the needs of the customer, usually the electric utility. I'll show you examples in a minute of 6 solutions. Success is like a stool with 3 legs. If one leg is weak or missing and you try to sit down, you'll fall over. You won't be successful. So it's really technology, standards, and policy. Technology today must be standards-based for successful integration and interoperability. And policy is the strongest driver to incentivize a customer to buy our technology. So we need to spend a lot of time with people that make policy, people that shape policy, okay? We want the grid to be self-healing, you know, so it can locate a fault, or it can detect a fault, locate a fault, isolate the fault, and restore service upstream and downstream of the faulted segment with no human involved. We also want the grid to be resilient, which means that when it's stressed with like an extreme weather event, we want to minimize the number of outages, and we want to, if we have an outage, we want to shorten the duration of the outage. We'll talk a lot about big data, new analytics, and what's very important is bringing together the information technology, IT, and operations, OT, operations technology, those 2 groups within the utility to support enterprise data management. So this is what I'm talking about with, you know, when there's so much emphasis on data today, we're hiring data scientists in the power system industry because there's so much focus on data, analytics, and decisions being driven by data. So we need to integrate the electrical and information infrastructures within organizations so that these 2 groups work together. Okay, that's very important. And at the bottom of the slide here, we're putting much more focus today on the distribution part of the grid. Okay, now what I want to show on this slide is 2 things. Shaded in light gray, where I say it's old grid, that's where we've been. Could everyone please mute themselves? Could everyone please mute themselves? Okay. Shaded in light gray is the intelligence we've been adding to the grid for many years. Shaded in light green is what we're doing today, what we're doing more recently. Okay. And that we want to show that we've been adding intelligence to the grid for a long time. What we're doing today, I call it, if you look at the top of the slide, I call it the smarter grid. Okay, making the grid smarter. For instance, on the bottom here, voltage control, I've shaded halfway. voltage is directly proportional to load. And so if I want to manage load, I lower the secondary voltage if I want to lower the load. We've been doing voltage control and reactive power control separate for many years. Today we integrate those two together. We call it integrated volt-var control. And that's the green part of this. If we look in the middle, where sensors, we've been adding instrumentation and sensors to the grid, but we have new specialized sensors we're adding today. So what I'm showing here, I oil from the transformer and bring it through that sensor, and I can detect gases dissolved in that oil. And each gas I detect is a failure mode that's occurring in a transformer. And I can detect up to 9 different gases that are dissolved in the oil of the main tank of the transformer. This is important because a failure is occurring. If we want to prevent a catastrophic failure, right? We want to prevent a big failure like an explosion or short circuit from occurring. So we monitor the health of the asset continuously. We'll talk more about the rest of those. So this is 6 holistic solutions that we've been implementing. Asset optimization is the health information from transformers and circuit breakers. Demand optimization is aggregated load. We're using that today as a dispatch tool in the control center. Adding more smart meters and two-way communications. Optimizing the distribution part of the grid. This is the most focused today is distribution and actually the strongest business case. Transmission optimization on the transmission part of the grid. We're doing a lot more work with phasor measurement units, right? What we call synchrophasors. We can get maybe 60 samples per second, where the typical SCADA type data, right? The typical data we use is every 2 seconds or 4 seconds. And then workforce and engineering design optimization. Really a lot of effort on the workforce. You know, when I was the IEEE PS president in 2006 and 7, and when I took over as president in 2006, the average age of the IEEE PS member was about 50 years old, and the average age of the IEEE member was 42. So we had an older group of members in the Power and Energy Society. We changed the name of the society in 2008. That we changed the E from engineering to energy. It used to be the Power Engineering Society. April of 2008 became Power and Energy. And we were emphasizing then that with energy, helping the environment, helping society. And now we've grown to, we've attracted a lot of young students and young professionals into the Power and Energy Society. And we're now the second largest society in all of IEEE. So we really need to emphasize the workforce, right? How can we attract students, young professionals into the power and energy industry? So these are the 6 holistic solutions. This is the roadmap of the 6, color-coded. So if you, like for an example, take a look at the blue, light blue boxes, that's distribution. You can see when I said that success depends on technology, standards, and policy, you can see why standards are so important. These light blue boxes could be from different vendors, but yet all of this equipment needs to be able to communicate with each other and exchange information with each other. They, you know, for that to be successful, the components have to comply with the same standard or sets of standards. Because you have components up in the office or control center, upper left, lower left, the substations, and lower middle, this is equipment downstream of the substation on the feeders, okay? There's 5 key components. 1 is smart meters. 2 is AMI, which is the two-way communications for smart metering. 3rd is geographic information system. That's the reference system for the network model for outage management and distribution management, the outage management system and the distribution management system. Sometimes we call the DMS the ADMS for Advanced Distribution Management System. So, you know, we use smart meters for a number of things. They give us power quality information. They give us voltage information, which is very important because when we do volt-var control, we flatten the voltage profile and we lower it, but we need to make sure the voltage at the very last customer on the feeder is above the standard for our country. Like in the United States, it's 120 plus or minus 5%. So 120 minus 5% is 114 volts. We want to make sure that the voltage is well above 114 volts at the end of the feeder. So we can ping certain smart meters at the end of the feeder to get the voltage, okay? Good example of integration. Now, the distribution part of the grid was designed for electricity flowing in one direction. If you look at the bottom of the slide, we say distribution controls and protection traditionally took advantage of and were designed only for power flowing in one direction. Well, when we started integrating distributed generation like photovoltaic panels, we have electricity now flowing in two directions. So we can integrate distributed generation at the transmission level, the distribution level, or the end user level. We'll talk more about the distribution level and the end user level. So some of the challenges with electricity flowing in two directions is, for instance, protection ratings may not match fault currents. When we set the protective relays, we first do a short circuit study. We model the grid in different places, and we say, if there's a fault, what's the expected magnitude of the fault current? Well, when we do that modeling, we only look at the source side contribution to the fault, you know, from top down to the fault. We typically feel that the load side contribution is negligible, and we don't consider it. But the problem is, if we have a high penetration of, say, rooftop solar or high penetration of PV panels on the distribution part of the grid, we could have a significant load side contribution to a fault. If a fault occurs when the sun is brightly shining, there could be a significant contribution. The other thing is varying fault currents due to distributed generation. The sun isn't always shining, right? The wind isn't always blowing. There's intermittency with the distributed generation, and that presents a problem. We'll also talk more about the stress on voltage regulation equipment. This is an example of a microgrid. We see many, many more microgrids being installed today because they help the overall grid be more resilient, right? We can decouple a microgrid from the main grid if there's a problem on the main grid, and the microgrid can continue to operate. So here's one. This was in a rural part of British Columbia in Canada. And you can see that this village, which is not near any utility, has residential load and industrial load. And they have hydrogen fuel cells, PV panels, hydro generation, and they have their base generation is diesel, which is pretty typical. The challenge is, though, the diesel is expensive. To get the fuel to a rural area is expensive. But also when the diesel generator operates, it sends carbon dioxide to the atmosphere, right? So what we want to do is minimize the use of the diesel and maximize the use of the other resources. And we do that with, in the upper left here, we have the microgrid controller. And it's a microprocessor-based relay, protective relay, with logic added to be the microgrid controller. Okay. Then this is an area in the Philadelphia, in the United States, Philadelphia area. It's an industrial development corporation, and we added GE added 2 microgrids there. And in addition to microgrids, microgrid automation control systems, and a distribution SCADA system, okay, to help manage the electricity in this industrial development zone. So a lot of companies now have located research area headquarters and research areas in what used to be an old Philadelphia Navy Yard. The U.S. Navy used to build ships there and repair ships there. And when it closed, it became a development area, okay? Now, how do we compensate for the intermittency? The sun's not always shining. When you come home and turn the lights on, you want electricity. But what happens if the sun's not shining? Okay. Well, energy storage we use, right? We call that bridging storage because it bridges the intermittency of the distributed resources. Also, we use fast start thermal generation. We're showing here in the middle a 60 hertz flex efficiency natural gas fired turbine generator. And these are fast starting and fast responding, okay? We also, about 3 years ago, was introduced to the industry an integrated package. It's called the electronic gas hybrid turbine, and it's 10 megawatts of lithium ion batteries packaged with a 50 megawatt natural gas fired turbine generator that's fast starting and fast responding. The other thing we're doing is we're distributing the control. So instead of all the information going to the control center and having centralized control, we've distributed the control to the substation, but also to the edge of the grid. And we'll now talk about what we call grid edge controllers, okay? And one example of that is what we call low voltage network. In other words, we install these on the low voltage network. Dynamic, because they're continuously doing set point control. Grid edge controllers, because they're installed on the low voltage network at the edge of the grid. And where we do this is when we have a high penetration of rooftop solar PV on the distribution system. So this is an example in San Diego, California. On one distribution feeder, many of the homeowners installed rooftop solar panels. In fact, over 35% installed panels. And this is an issue because in the morning, these homes are along the Pacific Ocean. There's humidity from the ocean that causes a fog, right, over the homes that blocks the sun. But as that fog burns off, the humidity, the moisture burns off with the sun, all homes begin generating at the same time, and the voltage on the feeder spikes and then oscillates. And the challenge is the tap changer in the substation is a mechanical controller, and its job is to keep the secondary voltage constant as the primary voltage fluctuates. Well, when you have a high penetration of PV panels, the volatility of the voltage increases, right? And the tap changer in a substation is working much more frequently because of the volatility in the voltage. And its lifetime went, in this particular case, went from 35 years to less than 2 years. It would have to be replaced. And that's a $50,000 piece of control equipment. It would have to be, instead of lasting 35 years, it's only lasting 2 years because it's mechanical. So the challenge is we want new applications of low voltage power electronics because they won't wear out, right? Like a mechanical controller. Okay. So some of the lessons we've learned, we're doing a much better job of forecasting the sun and the wind. Our thermal fleet, our generation, is higher quick starts, faster ramps, you know, to accommodate the intermittency. We still have some impediments or challenges like unobservable distributed generators that are behind the fence, right? That are outside of the utility service area, but connected to the utilities grid. The main thing though is we need to do a lot of studies. We need to model when, the question is like, what would be the impact of adding 5,000 megawatts of wind on the existing grid? Well, these are studies that were done to model the grid and see what the impact would actually be. So this is very important to, you don't just want to do that, add that generation without studying it and anticipating what the challenges are going to be. Okay. So the center for distribution, say is supervisory control and data acquisition. A SCADA system is the platform for all automation. A SCADA system for distribution is called an Advanced Distribution Management System, or an ADMS. And this is the central SCADA system model. On the right here, the SCADA server is the basic SCADA functionality. Supervisor control is remote control, and data acquisition is acquiring data from the field. The feeder automation application server has the special software applications to optimize different parts of the distribution system. Okay. On the left here, the geographic information system, remember that's the network model, or that's the reference for the network model for the ADMS. And what we do is we get information from the field, from the substation and feeder devices, bring it into the SCADA system. The operation of the distribution system is optimized, and new device control commands are sent out to the field. So there's 3 groups of software typically on a ADMS. There's the advanced real-time applications. These are running all the time, used by the operators. By the way, another fellow and I, we've done a full day tutorial for the IEEE PS just on an ADMS. And you can find that online. It's 5 PowerPoint files on the IEEE PS Resource Center. Okay, it's Dr. Jiwan Fan, Jiyuan, Fan, F-A-N, and myself. The 2 of us put together this one-day tutorial that we teach at many of the IEEE PS general meetings and the IEEE PS Transmission and Distribution Conference and Exposition. Next week, we have the IEEE PS T&D Conference and Exposition in Anaheim, California, okay, as an example. The second group is advanced analytical applications. These are run on demand and used for analysis. Okay, and then the third is what we mean ancillary, which means extra applications that the utility wants to run on the ADMS. Okay. So the goal today for utilities is a digitized grid. A fully digitized grid. The challenge, though, is that no utility can go from where they are today to make that big step in one step. It's just too much budget money and too many resources, people to get that done. So what we do is we say, well, let's put a roadmap together of steps to get there. So the question is, where are we today? Where's the utility today? Well, let's say they're at manual control and legacy methods. So what can we add as a first step? So we had remote control and monitoring. We had SCADA. We had customer status, trouble calls, and smart meters and circuit reclosers. That's a big step, big positive step, because the result is 28% lower customer minutes interrupted. So much better reliability with the distribution part of the grid. Okay. Next step is automation and visualization. We had distribution automation with power flow analysis. network visualization tools, and outage management prediction. And now we get 43% lower customer minutes interrupted than the base case, the base level. That's a big step also, okay? Then the next step is digitally enabled. We had network optimization, utilization, and asset performance management with outage analytics. And now we're much greater than 50% lower customer minutes interrupted than the base level. So this is a good example of a roadmap dividing into steps. The one goal here, though, is that at every step, we want significant benefits back to the utility, okay? Another example is a utility with 200 distribution feeders or circuits that wants to improve their reliability. They have 856 circuits total. So it's a big utility. 856 circuits. To try to automate all of those circuits would be a tremendous amount of money. But the question is, do we really need to do that? Let's study these circuits in detail. And we find that only 200 of the circuits account for 71% of all the outage minutes of the utility. So if we automate just 200 circuits, we address about three-fourths of the total outage minutes. That's a much better use of budget money, okay? So when we do automation, we're very much focused on data. And there's more than just one type of data in microprocessor-based devices. So I introduced these concepts here in 2003, 21 years ago, to in the IEEE PS magazine called IEEE Power and Energy magazine. It's a 10-page guest editorial in 2003. And I said, well, there's two types of data, primarily. First type I call operational data. And this is the information that we send to the control center for the operators because they need to use this data to monitor and control the power system. These are points like status points, analog points, circuit breaker open, closed, line current, bus voltages, transformer loading, alarm information, stuff like that. But the data that we also have available in these devices, but we aren't really using it as much as we should, I call it the non-operational data. And the reason is that the operators in the control center aren't really interested in it, but someone else is. It could be power quality, it could be maintenance, it could be asset management, could be planning, but not the operators. And this information is both points and files of information, like a digitized waveform from a relay, or circuit breaker contact wear information for maintenance, or like we talked about before, dissolved gas in the oil of the main tank of the transformer, or moisture content in the oil, okay? This is very valuable information, and I found that there's 25 to 30 other groups in the utility that have a need for this information, in addition to the operators in the control center. So this is comparing the operational data to the non-operational data. You can see operational is individual time sequence, their points, real-time or near real-time, and we use standard communication protocols to communicate it. The non-op data is both points and files, mostly historical. And if it's a file, we may need a vendor-specific format, proprietary format to extract it. Okay? So what's happening today with the Internet of Things? This is really the productivity revolution of connecting intelligent machines with big data and analytics with people at work, connecting people any place, any way, and any time for intelligent operation. And when we say connect, we mean communications, right? So, I keep emphasizing communications is extremely important. In fact, communications is the enabling technology that allows us to automate. We wouldn't be able to automate if it wasn't for successful communications, reliable, robust communications. It's very foundational, okay? And so it's fundamental here to the Internet of Things. But with our focus on data, then the question is, how can we get more value from the data? So these are areas of new analytics. It could be using more insight into the metering data, smart metering data, more insight with outage information, like a more accurate estimated time to repair from the utility, more insight with reliability. For instance, predictive vegetation management, or more insight with renewables. Could be the word we use today is orchestration of distributed energy resources. So we're talking about here distributed energy resource load orchestration, okay? Or electric vehicle penetration and impact analysis. And last is consumer, the end use customer. What's very important is we have to engage the end use customer when we put smart meters on customers' homes. But when we put programs together for the end use customer, we have to be aware that all customers are not the same, right? In fact, there's 5 different segments of customers, 5 with different behavior, right? And so if we put a customer program together, we have to take into account that there's 5 different behaviors of customers that we have to address, okay? So on the left here is a typical situation with many electric utilities, many organizations, of each group is very siloed with their own systems, their own, what we call IED, is Intelligent Electronic Device. This is a standard IEEE term that we created in actually 20 years ago when we were updating the SCADA standard for IEEE. Intelligent electronic device is a microprocessor-based device and a repository. So each group has their own systems, devices, and repositories, and there's very little sharing among groups, which isn't good, right? We have the same piece of data in the same database in 3 different groups. What we want is what we're showing on the right. Break down the silos, break down the divisions between the groups, and introduce a federated data mart and bring together all the users and all their data needs. We want to make sure that all the users have the data that they need from all the data sources in the enterprise. So the advantage of that on the right here in light blue, or the color cyan, light blue, we list all the data sources in the enterprise. And in green here is all the stakeholder groups, all the user groups in the utility that have a need for more data. So what's neat is the journey to digital transformation. This is pretty cool. This is what's going on today with grid modernization. This is a good summary of all the things I've talked about up to now in one slide. On the lower left, for many years, we were reactive, right? We waited until something failed, and then we reacted. The transformer exploded in the substation. We reacted, right? But by then it was too late. The damage had already been done. So it's kind of crazy. You think about why wait and be reactive? It's too late. Why not be proactive? Let's be smarter about it. And so we've gone through responsive, and today we're predictive. We're about halfway. The question is, what health information do we need about a transformer or a high voltage circuit breaker? And what analytics do we need to predict the failure modes of that asset, right? And that's what we're doing today. We're looking at any potential problem that we detect. We're analyzing that and we're saying, what is happening? What do we need to do to prevent that? We don't want a catastrophic failure, big failure, okay? We're applying machine learning to the data. We're applying artificial intelligence. We have many more use cases of the digital twin. And the goal is to be prescriptive and eventually autonomous, which is self-healing, self-provisioning, and extensive autonomous operations with limited human intervention. Okay? And I wrote the first chapter. I've co-authored 5 books, and I wrote the first chapter in a book called Big Data Application in Power Systems. So as I said, we're hiring data scientists. There's much more focus on data today. And the first chapter of the book is a holistic approach to becoming a data-driven utility. 2 key concepts: holistic approach, it means not group by group, but the whole company, enterprise-wide, and data-driven. Organizations today want their decisions based on data, okay? So this is a very good book. If you like data science, and especially data science applied to power systems, look for the book Big Data Application in Power Systems. Okay, so this is a good summary of what's going on today with grid modernization. I mentioned how important standards are. The landscape of smart grid is turbine to toaster, okay? Turbine meaning a power plant, toaster meaning your home. So everything in between, generation, transmission, distribution, end-use customer, is all smart grid, okay? So how do you draw all of that on one sheet of paper? Well, on the left here is the smart grid conceptual reference model that we developed. It's 7 domains, and the blue lines show how those domains interact with each other. But what's really important here, I mentioned how important standards are. There's over 100 smart grid standards with IEEE. There's also over 100 smart grid standards with the IEC, okay? So I chaired the board of a group of 25 industry experts for 5 years. And we said we need to do a better job of reducing the number of standards in smart grid to a small set that is much easier to manage for industry, right, for us. If we're doing a project and the question is what standards are relevant to our project, nobody can go through hundreds of standards. So this right here is very important. This is the 16 foundational standards for smart grid. Only 16, but they're very key standards, okay? So these are very important. When you're doing work, if you're developing a product or doing research at a university, or if you're in a utility and you're buying product for a substation, let's say, what standards are important to include. It's much easier now. You just look at this group of 16, okay? And what's nice is worldwide, on the top here, globally, there's one standard for control center to control center communications. one, Intercontrol Center Communications Protocol, or ICCP. From control center to field, there's just two. There's IEEE 1815, which we call DNP3, Distributed Network Protocol 3 in North America. But in Europe, for European suppliers, it's IEC 870-5, 101 for serial communications, 104 for network communications. And within the field, there's really one, IEC 61850 is the global standard, okay? So let me finish here with lessons learned. So when we started deploying smart grid projects, implementing them, we found that a holistic solution is a set of components integrated together. Well, the maturity of that solution is only as mature as the least mature component. And we found that some of the components weren't as mature as advertised and had to be field re-engineered or upgraded. But you know, we anticipated that because the real test for new technology is implementing it in the field. Second one is integration, interoperability. These are two key words, integration, interoperability. Success here is based on technology that's standards based. So we learned how important standards were. Third is testing. We need to do as much testing as we can in the laboratory before you get to the field, okay? Also, we learned how important project management is. A vendor could have very, very good equipment. The utility could have the best engineering team, but the project could still fail because the project manager was weak, was not very good, okay? So what's important is strong project management. And these projects have multiple disciplines within the utility. In other words, these projects include many, many groups, many disciplines. So the project manager has to have multidiscipline authority, right? Authority over all these groups. There needs to be consistent, what we call program management office, consistent program management guidelines, PM guidelines. And we need to build an A team, the very best team, with project and technical people. So we need to have a good team of engineers, engineering, but also project managers to be successful. And lastly, at the top here, the residential commercial customer is a major stakeholder, right? For many, many years, we never engaged with the customer because we didn't need to, right? A meter reader would go to the home, read the meter, the bill would be mailed to the customer and the customer would pay the bill. But now when we put smart meters on people's homes, we have to engage with them. We have to let them know what are the new services that are available now. What does this new smart meter mean? You know, you can now go to a website and see your electrical usage in your home from the data from the smart meter. Okay, so there's a lot of engagement that's required with residential commercial customers. Very, very important.
Battery 100%.
So let me finish there. I know we have a few minutes left. I think we have about 10 minutes left. I will stop sharing my screen, okay? And if anyone has any questions or any comments, I'll be happy to discuss those, okay?
Thanks, John, for that very insightful presentation. I'm sure Akhil has asked members to write any questions on the text message as text messages. So while we are waiting for any questions, let me just ask you about these microgrids. I know that microgrids are happening in different part of the world as pilots. What would be their future? You think that they are going to take over the traditional distribution network, or traditional distribution networks will evolve in a different way?
I think the distribution part of the grid, rather than being one overall connected grid, will be divided up into strategic microgrids, okay? And the reason is, think about if it's one connected grid, if there's a problem and the problem isn't isolated right away, it could get worse, right? And become maybe a blackout. So the resiliency of the grid isn't as good as, let's say we add some strategic microgrids, okay? And there's a problem on the main grid. All of these microgrids can decouple, right? They can island themselves, continue to operate, because the microgrid will have its own generation. Many times that generation is renewable generation also. And so we see many microgrids strategically being installed today to increase, to make the resiliency of the overall grid better.
Thanks, Roger. So the floor is open. If anybody wants to ask a question, either you can use the chat box or you can unmute your mic and straight away put that question forward to John.
I can't believe some of you should, with as many people as participating, you must have some comments or questions, huh? Don't be shy. Don't be shy.
Hey, John, this is Parani.
Yeah.
First of all, I would like to thank you for that talk. It was really interesting. So I did not have a specific questions, but on slide 24, you did talk about the feeder automation. And on the slide 30, I think you were talking about the customer minutes interrupted, how that has been reduced. So if you could give a little more, talk a little more on that, I'll appreciate that.
Yeah, so remember I talked about a self-healing grid, okay?
Absolutely.
And let me talk a little bit more about what I mean there and how we can make the grid more reliable, reduce the number of customer minutes interrupted. So I can install logic on the distribution part of the grid. And as soon as a fault occurs, rather than waiting for a human to react, or even a protective relay would react and typically open up the circuit breaker, right? Isolate the fault, but then many people would have an outage, right? And if the people, what we want to do is we want to minimize the number of outages. And we also, when we have an outage, we want to reduce the length of the outage. We want to bring electricity back to the people. So I have logic that I can put on the distribution part of the grid that automatically detects the fault, locates the fault, isolates the fault, and by isolating the fault, it opens up switches on each end of the fault, so that then what I want to do is restore service right away to all the customers upstream of the faulted segment and downstream of the faulted segment as soon as within 1 to 2 minutes, very quickly. And that really helps the reliability of the grid, because the only customers that have an extended outage are those on the faulted section of the feeder, okay? Without that logic, what happens is the feeder breaker trips to isolate the fault, and all the customers on the entire feeder have an outage for a long period of time, okay? So that's a big difference. We want to bring the logic automatically restores service to the customers upstream and downstream of the faulted segment, again, within 1 to 2 minutes, very quickly. And the only customers with an extended outage are those on the faulted segment. So that's what we mean by adding logic, adding technology to reduce the customer minutes interrupted. That's exactly how we would do that. Okay.
Yeah, great. Thank you so much for the explanation. I think we have some other questions on the chat.
I could see
Yes, for
those.
the, yeah. Do I need to read it for you, John, or is it comfortable? What is comfortable for you?
Akila, I can
Okay.
read the latest
Okay.
the latest research areas in smart grid. The latest research areas, one is energy storage, because the price of energy storage is still high. And we need to do a better job with research on chemistry, the chemistries. Because for instance, if we want frequency support, in other words, instantaneous support with energy storage, the best chemistry is like lithium ion for that. But if it's more in time, it's more, instead of power, it's more energy, the integral of the curve, right? If it's more peak load deferral, which is more time, longer time, it might be sodium sulfide. So there's different chemistries that are optimum based on the time of the application of energy storage. So that's one, is energy storage. Two is data science. You know, we're hiring a lot of data scientists and we're teaching them about the power system, and they're giving us new perspectives on how to optimize the grid from a data science perspective, perspectives we've never had before. And it's very, very innovative, very innovative. And so there's a lot of work going on in data science, machine learning of health information from transformers and circuit breakers, as an example. That the digitized grid, as I talked about, that's big. Okay. Those are a couple areas. Let me get to let's see, can we have smart device level data be integrated into smart using machine learning models? Yeah, in fact, there's papers out there. I've been accepting papers for conferences for 4 or 5 years now that apply machine learning to power transformer health information. And the machine learning is being used on that health information. And then we apply artificial intelligence with the analytics, and we use digital twin use cases. In fact, we're doing now the second edition of the big data book, and I added some new use cases. I added some new digital twin use cases in the revision of my chapter. Okay, so you can find articles online. Search on the internet. Search, machine learning application to power transformer health information. You should be able to find papers online, articles online. Yeah, controlling air conditioner temperature to reduce demand. We've been doing that for a long time with the electric grid. And what's interesting is you can take a central air conditioner, or you can take an air conditioner, and I can turn it off for 7.5 minutes every 30 minutes, and you don't notice the change in temperature in your home. The temperature gradient doesn't change, okay? So if I take thousands of air conditioners and I turn them off for 7.5 minutes, that's tremendous savings in load, okay? Without the customer knowing, after 7.5 minutes, I turn those back on and I turn off another group of customers for 7.5 minutes. So what I do is I block customers in groups, thousands of customers, and I turn air conditioners off. I cycle them for 7.5 minutes every 30 minutes. And we're actually using that today to dispatch generation. Okay. We're actually, instead of ramping a generating unit into a inefficient operating zone, I can use aggregated load as a dispatch tool. I could turn off thousands of customers for 7.5 minutes, lower the load, instead of ramping a generating unit up to an inefficient operating zone. So it's not only being used for load control, but we're using it for dispatch, generation dispatch also, okay? Well, what's the distribution, this last question, the distribution system, or the second to last question, the distribution system, we designed it to be electricity flowing in one direction. It was, for years, it was very simple, right? The architecture, the topology was radial, right? From the substation to the last customer. There were no normally open tie switches at the end of the feeder. It was radial. It wasn't mesh. Electricity flowed in one direction. And it was very simple. We didn't need a separate SCADA system for distribution. There was no need for an ADMS, okay? Then we started integrating distributed generation. Wow, what a difference. We have electricity flowing in two directions on a grid that wasn't designed for it. We have protection settings that aren't correct, as I talked about. We have voltage regulators that are mechanical devices, tap changers that are operating too frequently. You know, their lifetime is much less. We have to replace them much faster than we ever did before. We have possible congestion on distribution that we never had before, okay? If I'm a worker and I go out to the field to do work on a distribution feeder, I used to be able to open the upstream device and I'd have a de-energized work situation because electricity only flowed in one direction from source to load. Now, if I open the upstream device, I still have an energized line because I have PV panels downstream connected to the distribution grid feeding generation upstream. Okay, it's still energized. So it's much more complicated than it used to be. So these advanced distribution management systems are critical today, critical to manage the complexity of the distribution part of the grid. And it's only going to get more complex with increasing penetration of distributed generation. Yeah, the feasibility of achieving greater than 53% CMI. So remember, 53% is just the improvement in what the base level was. So if the base level is manual control, it's pretty basic, right? The base level is, so a 53% improvement over manual control is very realistic for a developing country, because we're talking about improvement here. And if your existing situation hasn't implemented a lot of technology or intelligence, you can easily achieve 53% improvement. So I would say yes. What's very important here is putting a lot of thought into a strategic roadmap. You know, what for a developing country, first of all, assessing where are we today, like Sri Lanka, where are we today with our technology, okay? Like the example I showed, it was manual control and legacy methods. So very little had been installed in that country. It was manual control, legacy methods. So then the question is, what's the first step? Okay. And the first step has to be reasonable with budget money and people resources to do the installation. What's the second step? What's the third step? And then where do we want to end up? What's our goal? And we can take many steps to get there, but every step should have significant benefits. That's what's important. So yeah, achieving 53% lower CMI is very because it's an improvement over where you are today. Okay. Protection schemes, a couple of new research areas are, and you can search on the internet for this. virtual protection. Virtual protection. Instead of having individual microprocessor-based devices for protection, the protection settings are virtual. There's software in a server. Okay? We don't have individual protective relays, microprocessor-based devices anymore. That's one. Second one is settingless protection. The word is settingless, settingless protection. A very famous professor here in Atlanta, where I live at Georgia Tech, his name is Professor Miliopoulos. He's the inventor of settingless protection. And you can find his articles and papers online. Okay, that's another research area in protection. Those are two primary ones for protection. And then for battery energy storage, I would look online for Duke Energy and the Mount Holly microgrid. Okay, and the energy storage in that microgrid, very innovative protection schemes. There's public articles that have been written about the innovation with the protection. So think about Duke Energy and Mount Holly, Mount Holly, HOLLY microgrid. For instance, there was an article in Transmission and Distribution World magazine, T&D World magazine, about the Mount Holly microgrid and the innovation that was done with the protection schemes for battery energy storage in that microgrid. Okay, that's a good example. It's public information that you can find online.
Thank you, John. But I think we have one raised hand from Misal. If you
Yeah,
want.
thank you,
Yeah.
Akila. John, two questions for you. When looking at the future, I mean, do you think microgrids can survive on its own without a central grid or a central system? And the second one, where do you draw the boundary of the microgrids? I mean, what is the size of it when you consider? I mean, if you consider a small country, that itself can be called a microgrid. I mean, so where do you draw the boundary line on that?
Yeah, I would say there's no question that the microgrid, we designed microgrids for two types of operation. One type is connected to the main grid. Okay, so it's operating connected to the main grid. And the second form of operation is islanded from the main grid, where it's disconnected and operating on its own. So they're designed to operate in both ways. So it's very realistic for microgrids to operate for long periods of time, islanded, disconnected. We have examples in the United States of when we've had, serious disturbances, like parts of the United States are blacked out. Okay, like in 2003, we had a very, very extensive blackout in the US and Canada. And more recent ones, there were microgrids disconnected from the main grid that continued to operate. They never had any downtime. Okay, so that's very realistic. In terms of the size of the microgrid, I would say, you can, like in Sri Lanka or United States or different countries, the microgrids are sized based on what the local needs are. So there's no set rules. It's very much custom to the specific situation. So I would say there's no set size. The one thing that, couple things in the US is the utilities look for strategic locations for microgrids. In other words, areas where you want high reliability, right? There's something going on and you want very high reliability, because a microgrid can give you that increased reliability. Second would be where you want to implement distributed energy resources. Maybe, you know, photovoltaic, you have an ideal location for photovoltaic panels or an ideal location for wind. Typically, the microgrid, we want high reliability. We want to be able to have enough generation so when it's islanded, it can continue to operate. And ideally, we'd like a lot of that generation, most of it, all of it, to be renewable, right? Either PV panels or wind. So in terms of sizing a microgrid, we say, well, where do we need high reliability? How much is that load there? And also, where are ideal locations for us for distributed energy resources? So utilities have a set of criteria like that, and that's how they locate where microgrids should be. Strategic locations is based on the criteria that they put together. But there's no set size. It really depends on unique conditions that you have. And even with the same, like Commonwealth Edison in Chicago has put in 5 strategic microgrids. But these 5 microgrids they're strategically located based on their criteria, but they're all different sizes based on what their needs were in each location. Okay.
Thank you. Understand. Yeah.
Thank you very much, Sean. I know it's a tired Q&A, so but if anyone has one last question, so thank you very much for being engaged in the Q&A, and I think from your expertise we can get more. So I hope that's it. Okay, thank you very much, Sean. Actually, from your discussion and also from your presentation, what we kind of get the main idea is we have to be open for new technologies in grid, and also we have to do our R&D, regardless of it will be implemented in tomorrow. It will not be implemented in tomorrow. Soon we discovered something, but we have to do our test, as you said, the testing and all the criteria that we want to have in our grid will be satisfied at the end of the outcome of research R&D. And also I appreciate you mentioning about PS contributions for these developments of smart grids and other technologies in power systems, and also about the standards. So it's very important to understand the importance of standards, and also to learn how to follow them and get more insights for our projects and even for our R&D. So thank you very much. And it was very informative and very detailed for us to get some practical ideas about it as well. So without making your early morning too much, staying with the technical stuff, so I really want to thank you for letting us get this opportunity to get the information and knowledge from you. And I hope that the audience got the advantage of our session today. And looking at these interactive sessions in Q&A, I really believe it was a good session for all. And I really thank, on behalf of IEEE PS Sri Lanka chapter, and which in collaboration with we conducted this session is IEEE Central Region subsection, and also ISL Electronics and Telecommunication Engineering Sectional Committee. On behalf of all of these organizers, I'd like to thank John for allocating this time to conduct this webinar on behalf of our members and also our community in power sector. So thank you very much, John. I hope to see you again soon. So
Yeah.
thank you.
Thanks, Akila. Thanks everybody. And I hope to see you soon, Akila. Yeah, somewhere at some conference or somewhere.
Thank you very much. Yeah.
I really appreciate the opportunity today. Okay. Good luck to all of you with the things that you're doing. I wish you the very best of success. Okay.
Okay, we'll keep in touch for the future activities as well with you. Thank you very much.
Thank you.
Sean.
Bye-bye.
Have a good day. Okay.
All right. Bye-bye.